to log in, so let's kick off. Once again, I'm Adam Green from ATA Engineering. I'm Business Development Director here, and I'm joined by Chris Stoich, one of our engineers in our STAR-CCM Plus CFD team. What we're going to talk about today is really the new release of STAR-CCM Plus and some of the new features in it in 2506. And so we'll get into that. But for the first few moments, let me just introduce ATA to any of the audience who don't know us. We are, okay, that's it. We're an engineering services company, really providing high-end and high-value services to a variety of industries. Aerospace and defense are some of our key ones. Spacecraft and satellites are another one of our industries. And industry and mining and themed entertainment are also areas that we work. But really, it's aerospace and currently spacecraft that is the mainstay of our business. And we are an employee-owned small business. We have over 220 people, and we are a very skilled bunch of folk in terms of skills in mechanical engineering overall, and also degrees and so forth. With over 44 PhDs, over 170 masters, we really have a very elite team of engineers doing the hardest problems. And we have offices throughout the US, mostly in areas where there is a high volume of space and aerospace work. And if you look at the map here, you can see that we have a few locations where we have a locked symbol on, and those are locations where we actually have secure computing facilities to do computing for our aerospace ITAR clients or beyond who need secure computing facilities to do services work. But you can see we have offices throughout the US. I'm calling from Boston today, and I know Chris is in San Diego. And really, one of the things that being a small business and employee owned is that all of us take pride in making sure that our customers get very good service and good satisfaction. So we really strive for customer delight. And we've been around doing this for 25 years this year, which we're very excited about. Prior to that, ATA was a division of a company called SDRC, which created tools such as Ideas and Unigraphics and some of those. And so in 2000, ATA moved from SDRC to become ATA Engineering. And since then, we've grown as a company in terms of our engineering services. And we also became a value-added reseller of VAR for Siemens software in 2016. We achieved gold status for that, and then in 2018 we started to sell STAR-CCM Plus and HEEDS. So, and even before 2018, we were using STAR for our engineering services work, and hence, the skill level of our support teams is extremely high for working with all our clients. And we also in 2021 and growing in 23 and 25 have become the Siemens partner of choice for selling test and measurement hardware and software from Siemens, which is always very exciting. And so in terms of what we do design, analysis, and test, and really using a lot of Siemens tools to do that. And so we really kind of integrate complete solutions in those three domains, basically tackling a lot of hard problems that people like NASA and JPL come to us for help with, and so we are viewed as very top end in terms of our skills and our value that we add to clients who are struggling to do difficult work. And doing all of these things, design, analysis, and test, obviously while we're doing it, we're doing a lot of test work, and these are some of the things that we do: very advanced methods, GVTs, acoustics, flutter. There's just a lot of pieces of the test work that we do. But along the way, we also use a lot of Siemens tools. And so we are specialists in Siemens Center as a whole, Team Center, NX CAD CAM, FEMAP, Nastran, HEEDS, and AIMSIM, among others. So we use all of these tools in our regular engineering services work, and that really puts us in good stead to help support our clients who buy from us using these tools as well. So, for instance, in our STAR team, now we have 9 9 engineers working on STAR all the time, who are also working with our clients to make sure that they can get the best from it too. So let's talk a little about our subject today. We're looking at STAR-CCM Plus 2506, the new version. And Chris is going to talk about these things. If I can find my mouse, there it is. These new features, but really from a list of about 130, he's picked out the ones that we find of great interest to us, and he's going to talk about those in more detail. I won't read them out because you can read them too. But one of the things that is not on the list that Chris is going to do that is very exciting, another one of those 130 features there, is a new technology called ray tracing, and so STAR-CCM Plus obviously deals with CAD data, deals with computer models of really almost anything, and often the results from a viewing point of view sometimes look as if they are CAD data. They look as if they're a little sterile compared to Hollywood kind of thing. So ray tracing is it's not new, but it's new in STAR, that lets you really deliver photorealistic images of CAD models and CFD results. So if you look at something like this tank, that shows up made of stainless steel. If you're looking at that as a CAD file, you might not see that. So this is actually a STAR model, fully ray traced, and looking very realistic. And with screenplay within STAR, you can also apply the ray tracing and the geometry selection to really create very photorealistic videos and still frames. And so this is a little different to GPUs, which is something Chris is going to talk about in his presentation, where GPUs are based to accelerate the mathematics of solving. But in this case, this uses a specific part of GPU, mostly desktop GPUs, for ray tracing with RT cores from NVIDIA, and really developed for the gaming industry, but have a specific hardware algorithm on a chip to let you do ray tracing very quickly, and at very low cost. If we look at some of these examples, like basically it runs on the GPUs, but in that example, that was run on an NVIDIA GeForce RTX 3070, that last one, which is about a $200 desktop graphics card. They have ray tracing cores on board to be able to do this. So this could be done by everybody, in our audience, and everybody who is using STAR could certainly, add a decent graphics card and be able to do ray tracing to all of their models to add a level of photorealism. And so when we look at this next video, really, I hope this gives everybody a feel for what can be done. Now, remember, this is a STAR model and the results from a STAR simulation. So it's a CFD model, but really every part of it looks very photorealistic. Now we can tell it's still a computer model. It's not that realistic, but it's still a lot better than we've seen previously. Let me actually play that once more because I think it's interesting. Obviously the car's ray traced, but also the water that the car is passing through has reflections as well, and all of the pieces of the visuals are applied. So I think it's very exciting, and I hope that the members who are listening and people who are watching the recording of this will try that out. So without further ado, over to you, Chris.
Thanks a lot, Adam. Can you see my screen?
Yes.
Great. All right. Thank you so much. Yeah, so as Adam mentioned, a lot of new features introduced in STAR-CCM Plus 2506, roughly 130 if I counted correctly. I don't have time to go through all of those, but I picked out 4 that I thought were worth mentioning. They may not be the 4 most, impactful features to you, but I thought that they're interesting, worth pointing out, and in the case of DFBI Kinematics Solver, kind of a fun example of what you can do. So I'll start with the Parametric Surface Morpher, which I'll go into more details about this later, but it allows an analyst to parametrize the geometry for which no CAD exists and the analyst only has access to, a tessellated surface mesh. So this kind of opens up the pathway to doing design trades or even design space exploration. Next, I'll just point out a small but I think impactful feature called the virtual disk wireframe highlighter, which allows a user to identify costly input errors when setting up blade element method simulations. I then will discuss the DFBI Kinematics Solver, which allows the efficient solution of complex gear systems through kinematics motion coupling. And then I'll give a GPU status update, just showing kind of where STAR-CCM Plus is along the road to porting over to GPU computing. Okay, so right, Parametric Surface Morpher allows parametrization of tessellated geometry. So to arrive at a good design oftentimes requires that there be a back and forth iteration between CAD design and analysis. And ideally, an analyst performing the trade studies might have access to the CADs that he can make changes to that geometry. Unfortunately, sometimes only tessellated geometries are available for making are available, to analyze, and this can make design iteration on the geometry at least very difficult or even impossible. Luckily, in STAR-CCM Plus 2506, the analyst is given the capability to parametrize tessellated geometries, enabling them to make geometric design trades. So the example that I'm going to use here is just this this drone here that I pulled off GrabCAD. And I'm going to use this surface morpher, this parametric surface morpher, to change the length of the wing of this tessellated drone geometry. So this is very easy to do. I first just needed to identify the displaced part. So in this case, it's just the tip of the wing, and I'm gonna say this is the part or the surface that I'm going to displace. And then I identify the floating surfaces. Those are the surfaces that are attached to the displaced surface. So as I move that wingtip out, of course, the wing surfaces need to float along with that motion. And then there are also the fixed surfaces. So you can specify these, but by default, STAR will just assume that anything that is not in the set of displaced surfaces or floating surfaces is a fixed surface. Then specify the translation vector and the coordinate system along which that translation occurs. So the example that I'm using here again is this wing of this drone. And shown on the lower right, I just show, okay, I've got my parameter morph length, is what I call it. So at 0, we've got the wing with the original length, and then if I put it at 0.5 meters, then it extends the wing. And this drone has a wingspan of approximately 2 meters. So this enables me to make design trades, or I can plug it into STAR's design manager and do a full-on optimization. So in this case, I'm doing a multi-objective optimization. The results here are kind of trivial because I'm only varying this one parameter, but with this parametric surface morpher, I was able to take this tessellated geometry and really understand this design space and understand the trade-off of lift over drag versus wing moment. So anyway, I think this is a powerful capability, allowing an analyst to do something that they could not previously do with only a tessellated geometry. Okay, so I'm going to move on to the virtual disk wireframe highlighter, which really, I think, increases the usefulness of the blade element method. So I think we can all say that helicopters, rotomachinery, are complicated machines, and performing a simulation in which you have to, build a mesh that is resolved down to the helicopter blade, and capturing the flow physics there can be expensive. The blade element method is a powerful tool that allows you to skip modeling the blades explicitly, and allows you to accurately analyze the complex flow field associated with helicopter rotors. It models the spinning rotor as a distribution of momentum sources that are dependent on the rotor geometry and local flow conditions. So this allows you to achieve the accuracy of capturing the flow physics around a helicopter rotor without the expense of a body fitted mesh in a rigid body motion time accurate simulation. So blade element method provides efficient and accurate predictions. Shown on the right is kind of a steady state simulation that I did using blade element method of this helicopter here. But to achieve that accuracy, there are many inputs required to use the blade element method. So what that means to me a lot of times is there's a lot of opportunities for me to make a dumb user input error. So this disk wireframe or this virtual disk wireframe highlighter was implemented to kind of help you identify those input errors before running a simulation, and just I think really makes the workflow much more effective and efficient. So here I kind of just have this screen grab kind of showing all of the inputs associated with the virtual disk model, and here you can see that the highlighter shows that okay, our helicopter blades are obviously not right. They're crashing into the fuselage. There's only two of them. They're way too big. What do we need to change to fix it? So one of the things was change the pitch angle. Now that looks correct, but these blades are still like way too fat. There's only two of them. What else needs to be changed? So I go up to chord distribution. I find that I specified, that they're 0.6 meters instead of 0.06. So I change that. I go back, check the highlighter. Okay, these look like helicopter blades. Now I just need to change them because I wanted 4 of them. And so through all that, I was able to quickly, verify that, hey, my helicopter blades weren't accurately described by my inputs. I need to make some changes before running a simulation, being confused by the results and wasting time. All right, so next I'm going to talk about the kinematics solver in the DFBI solver. The DFBI solver, or dynamic fluid body interaction model in STAR, allows you to simulate the motion of rigid and flexible bodies, and the resulting interactions between those motions, between those bodies and fields around them. Yeah, the DFBI allows you to model interactions between 6-off bodies, and any continuum, be that a flow through traditional CFD, or smooth particle hydrodynamics, electromagnetic field, a solid stress field, or DM particles. as part of the DFBI solver, STAR gives you couplings which enable predictions of complex interactions between either multiple bodies or the bodies and continuums. An example is shown on the right, where we've got, these two boats moored to kind of this dock, and the couplings are the ropes you see between them. So you can see the complex interaction between the large boat and the dock, and then the small boat and the large boat as those couplings are being pulled um, and yeah. So the kinematics solver with introduced in STAR 2506 enable complex gear trains to easily be built. So not the example that I'm showing on the right, but the interactions between gears. So the kinematic solver allows for revolute joints, bracket joints, gear joints, or planetary gear joints to be modeled. Shown on the right is the example of a planetary gear system. The way that it's set up is there's one body driver that's used to drive the motion of the kinematic system. And on the right there, I think that's the center gear. And then all other motions are based on relationships, either direct or indirect, to that body driver. So those are the couplings that I discussed earlier. So this solver was developed primarily to solve powertrain lubrication problems, but can be applied to any complicated geared system like a wristwatch. So as I was thinking about a demonstration case to show here, I thought it might be fun to try and build like a stopwatch or something. And just as an aside, I found this blog on the lower portion of the screen there, that if you're interested in how watches work, the author does a very good job explaining it with an interactive blog, and I had a lot of fun learning about that. So on the next slide here, I show my ATA stopwatch that I built. So using kind of watch jargon, the fourth wheel is what I'm driving, and that's the second hand there that's rotating at 1 revolution per minute. Sorry. And then all other gears are based on their relationship to that driver gear, ending with the minute hand, which is rotating at 1/60th revolution per minute. And then I just used STAR's screenplay feature to animate this, so I could spin it around and show you how the gears work while it's solving. So yeah, and I'll finish this off with just an update on the porting of STAR to GPU. So shown here is a list of really the major models and solvers that have been ported already, allowing computation on GPUs. The most recent addition in 2506 is the mesh-free discrete element method, or mesh-free DEM. And that is typically a very expensive computation. So this is a big step forward in increasing the efficiency of doing DM simulations. One thing I want to note, because I don't think it's obvious, is that STAR has a preferred set of, I guess, GPU cards that it likes to run on. For NVIDIA, that's the Volta, Turing, Ampere, Hopper, and Ada Lovelace. And on AMD, that's the Instinct MI100, MI200 series. So a little bit more about the GPU-enabled mesh-free DEM. So this, of course, increases efficiency over running on CPUs. So shown shown on the lower right is just a mixing case where we've got two different types of particles, which are mixing, and that simulation was run twice, once on 64 CPUs, and then once on an NVIDIA A100 card. And the NVIDIA A100 card showed a 1.8 times speed up over the 64 GPUs. Just some notes, the implementation has some limitations still. All boundaries must be a wall, and all particles are injected, pretty much at the beginning of the simulation, and injectors, have not yet been ported to GPUs. Also, this is with the mesh-free DM solver, so there's no interactions yet with continuums, so you can't model, the interactions of these particles with the air in this drum, for instance. This is compatible with all rigid body motions and DFBI, so you can have, see what these particles are doing to your gear train or something, if you want. And then majority of the DEM models are ported to GPUs, so that includes, a number of different particle geometries, as well as, wall interactions. And yeah, so that's the end of my update, Adam. Do you want to take the screen back, or just take this?
Chris, no, we can leave it there. I'll throw it open to the audience. Does anyone have any questions for any of these things? Chris, can you go back to the CPU slide you just showed there?
Yeah.
So just to clarify this slide, everything on here is GPU enabled, right? The new ones are in bold on the left.
Sorry, I bolded the ones like the high level stuff. So for instance, real gas equation of state, that's kind of just the title for the 7 examples of real gas equations of state to follow.
All right. So all of these are supported in GPUs currently.
Right, yeah.
Excellent. All right. Thank you. So anyone in the audience got any questions? If you want to type it into the chat or put your hand up and we can unmute your mic. All right, I think we're good then. We appreciate your time, everybody, this afternoon. Thanks for joining, and we will wrap up this webinar. Thanks very much. Have a good day. Bye-bye.